So I really do want to make some more progress than we did last time. We didn't really get back to the analysis of the select sort or select algorithm. We just got some of the preliminary things out of the way, and some of the people afterwards asked me, are we going to do the full analysis? And the answer is yes. We're going to hopefully do it today, and more so. So let me just quickly remind you, we're talking about the select algorithm, where you have a set S and you're looking for the kth smallest element. And the main point about the algorithm is that you pick a splitter, AI, and then you find the elements that are smaller than AI and the elements that are larger than AI, and you do some comparisons. And we put this up on the board. I put this up twice already, so I'm not going to put it up again. Hopefully everybody has it. The material, this material is in the book, chapter 13. I think it's section 3 or 5 through 7. Well, somewhere around there. If you look in the book, you'll find it in chapter 13. At any rate, so that's the select algorithm. And last time we said the worst case running time for this is n squared if n is the size of S. And what we're going to do is now randomly pick the splitter. Okay? So it's not at all clear why choosing randomly is helpful. And then last time what we talked about was really setting up the problem. What is it that you can derive? What is it you can learn about a randomized algorithm? And the thing that we're going to focus on is what is the expected number of comparisons that are done in this algorithm as a function of the size of S. Okay? And we want to derive something about the expected number of individual comparisons between numbers as a function of n, the size of S. And then the next thing we did last time was we started talking about the geometric distribution, because that's going to be critical in the analysis. And the geometric distribution basically, the form is, the setting, that's the word I'm looking for. The setting of this is that you have individual trials. A trial has either a success or a failure. You can think of it, let's say, as flipping a biased coin. A trial has a probability of P of being successful and probability of Q, which is 1 minus P, of being a failure. And then we can talk about what is the number of trials, which is the number of trials until success. That means including the successful trial. And if you were to take an actual biased coin, which has a probability P of success, and flip it until you have a success, and record how many trials that was, and then do that again, and do that again and again and again, and then take the average over what you see in those experiments, then that would be an empirical way of deriving the expected number of trials until success. But analytically, it's equivalent. This is the form that's absolutely equivalent to this, which is J, which is the actual number of trials, and we're summing from J equals 1 to infinity, times the probability that J trials, you had J trials until success. Well, you had J minus 1 that were failures, so you have Q to the J minus 1, and then you have the one that's a success, which is P. So if you can solve this sum, you have analytically what is the expected number of trials in a geometric distribution until success. And a word that I didn't use last time, but I should have, is mean. So when we say an expected value, another word for that is mean. The mean number of so the mean of the geometric distribution, the mean number of trials until success, you can solve this analytically. It's 1 over P. We didn't do that last time. I pointed you to some notes that I have on the class website that do that derivation. There's a cute little trick in there. So you can look at that. The book also does that somewhere in chapter 13. But it's kind of disappointing because right where you need the trick, right where you need the cleverness, it just jumps to the conclusion. I don't know why they did that. That discussion in the book is no better than just telling you that it's 1 over p, because you don't really see the full derivation. But the notes on the website do that. Okay, so this is about where we got to last time. And now we want to get back to the actual analysis of what is the expected number of comparisons that are done in this algorithm. All right? And so for that, well, just to remind you what's happening to S as the algorithm proceeds. S is getting smaller and smaller. You're calling this right down here where we have the recursive call. Everybody remember that one? We had two possible recursive calls. What you're calling on is a set that's getting smaller because you either got rid of only AI, the splitter, or you actually got rid of some other elements. If you recurse on S minus, well, anyway, you may be getting rid of more than a single element each time. And so S is getting smaller at each recursive call. So because S is getting smaller, we can define phase J of the algorithm, or the execution of the algorithm, to be the time during which the cardinality of S has this property, n to the 3/4 to the j plus 1, n to the 3/4 to the j. Okay? So this is 3/4 is less than 1, so 3/4 to the j plus 1 is smaller than 3/4 to the j, right? So the size of S is getting smaller and smaller as the algorithm proceeds, and there may be some time during the algorithm when the size of S is in this range. It's also possible that the algorithm skips by the phase J, but this defines what I mean by phase J. If there's any time in the algorithm where the size of S is in this range, then the algorithm is in phase J. Okay. Next definition, and if anybody has any questions, what's the most obvious question about this? I'm just thinking, yeah.
Why 3/4?
Oh, yeah, what's it for? It just seems like some silly definition. I'm sort of expanding your question. Why 3/4? Why phase J? Why anything? Yeah, and the answer is, yeah, you don't yet see. It's just, for the moment, it's just some definition. Was that your question, too?
I was going to say how many times can you see in phase J?
Well, we're going to look at that, actually. That's part of why we're defining this, yeah. And the only thing I've said so far about how many times how many iterations, or recursive calls, you're in phase J is that it's possible that it's none. The algorithm could possibly skip by it, but if the cardinality of S is in this range, then we say you're in phase J. Okay, now I'm going to give another definition. So this is one definition. Now here's another definition. Define AI, that's the splitter, to be central if AI is larger than larger than 1/4 of the elements in S, and smaller than at least 1/4 of the elements in S. Okay, and when I'm talking about the splitter AI, we're talking about in a particular call to select. For a particular call, there is a particular S, and in that call, the splitter AI is picked randomly, and if AI is larger than 1/4 of the elements of S and smaller then a quarter of the elements of S, and we're talking about the current S where that splitter is picked, then we say it's central. So what does that picture, what does it look like pictorially? Let's say this is S, and even though S is not sorted, let's think of it as being sorted. So here are the small guys, and here are the large ones. And a quarter, roughly like that, roughly like that. So AI is being picked randomly, and we're saying that if it falls in this range, it's central. This is where AI is central. Okay? So now I can ask, with that definition, I can ask the following thing: what's the probability that AI is central? It's what? 50%, or half, okay? Yeah, because this is half the range, okay? This is a quarter of the size, this is the quarter of size. So it's the probability, and since we're picking AI randomly, which means every choice is equally likely, the probability that when you pick a splitter randomly, the probability that it's central is a half, okay? So probability of randomly picked AI is central equals a half. All right, so now let's think of picking a splitter as a trial. And success will be if the splitter is central, and failure will be if the splitter is not central. Okay, so we'll pick the splitter randomly. If the splitter is central, we call that a success, and if the splitter is not central, we call that a failure. So now what we can ask is, what is the expected number, or the mean number of splitter picks until a central splitter is found, or central splitter is picked? Okay? Who can answer on this side of the room? Okay, who can answer on this side of the room? Yeah. It's 2, right? Because here we have it right over here. It's a geometric, that's geometrically distributed. P is equal to a half, so 1 over a half is 2. So if you pick randomly, the expected number, the mean number of picks that until you pick a central splitter is 2. Okay, and you can try this at home. If you, I mean, this is a half is like what a coin is. Okay, so I mean, this is just the geometric distribution. But a coin, let's say it has, it's a fair coin, so the probability of being a heads is a half. And you just do the experiment. You flip it, maybe it's a heads the first time, so then that's a 1. You flip it, maybe it's 3 times this time until you get the heads. So that's 1 plus 3 averaged to 2, and so on. And you keep doing that until you get tired after about 20 or so of those. And even by 20, you should see that the average pretty much converges to 2. And what this does is show this analytically. So the mean number of picks of a splitter until the splitter is central is 2. Okay? All right, next thing to point out is when you pick a central splitter, well, you've picked a central splitter, and now what happens? Remember, in the algorithm, if what does happen? Good point. Okay, let me just ask one other question. What is the expected number of comparisons done until a central splitter is picked. Okay, so again, your iteration, you're in a recursive call with some particular set S, not necessarily the original set, but as we're going on, this S gets smaller and smaller, and you pick a splitter, okay, and you do some comparisons to find that splitter, and then that splitter is either central or it's not, okay. If it's not central, maybe it'll be central on the next pick, and so on. So what is the expected, what can we say about the expected number of comparisons done until a central splitter is picked? It's a bit of a tricky question, but who has the answer?
It's 4.
It's what? 4? Well, it's got to somehow have something to do with the size of S. It can't just be an absolute number. Okay, we're doing comparison. When you pick a splitter, you compare everything in S to it to find S minus and S plus. Okay, so you're doing character comparisons. I keep saying character, but I mean number comparisons. You're comparing, yeah.
Would it be 2S or 2 times the size of S?
Yeah, that's the answer that I'm looking for. It's less than or equal to 2 times the size of S. And the reason that I say it's a tricky question is because, let's say because this is sort of the right answer when you first think of it. But then you might see there's a little bit of a refinement, because if you pick a splitter and it's not central, yet it still might, it still gets rid of some elements in S. So the next time you pick a splitter, your set is a little bit less, is less than S, so you're actually doing fewer comparisons the second time. But it's fewer, not more. So you could say, well, the first time it's S, and then the second time it's less than S, and if there's a third time it's less than S, less than that as well. So each one of those is less than S. And the expected number of flips, the expected number of trials until you're central is 2. And so therefore, the expected number of comparisons done until a central splitter is picked is less than or equal to 2. To 2 times the size of S. Okay. So that. And that's the level of precision we'll live with anyway. But everybody see that if you really want to do this really precisely, and that's why the question might have at first seemed tricky, it might be, well, it should be strictly less than 2S. Because if you get the central splitter the first time, it was S comparisons, or S minus 1. And if you didn't, then you're moving on to a set that's strictly smaller than S. Okay. Now, the next conclusion that I think we want, and I got stalled on a minute ago, is that when you pick a central splitter, what phase do you next move to? So that's what we want to analyze, and for some reason I don't have it in my notes here. But let's think about this. So when you pick a central splitter, okay, yeah, well, we're looking for the kth. We're looking for the kth smallest at this point. Now we don't know what k is, okay, but in the algorithm, you're picking a splitter. Maybe it's here, happens to be central, and then you look to see all the elements that are smaller. It's here, okay, and all the elements that are larger. It's over there, right? And then depending on what k is, you get rid of, well, either you're finished. If you just happen to, if AI happens to be the kth smallest, that's fine, you're absolutely done. Or you're getting rid of either this side or that side, right? That's what's happening in the algorithm. You're recursing either on S minus or you're recursing on S plus. So you're recursing on the elements that are smaller than AI, or you're recursing on the elements that are larger than AI. Okay? So if it's central, what can you say about how many elements you're getting rid of? That is, how much smaller is the set that you're recursing on than the set you're working on? Yeah?
It's at most going to be 3/4 of S?
Yeah, you're getting rid of at least a quarter. Because if you recurse on this side, you're getting rid of this quarter at least. If you recurse on the other side, you're getting rid of the other quarter. The point is, if you're central, you're at least getting rid of a quarter of the elements of S when you're in your next recursion, and next call to select. Now, why is it important to be central? If you were way out here, depending on what K is, well, you might get, depending on what K is, you might get rid of a huge section, but you might not. You may be only getting rid of the other side. So since we're not using K in the analysis, we're just using the size of S in our analysis, all we can say is that when the splitter is central, you're definitely getting rid of at least a quarter of the size of S in your next recursive call. So let me write that down. When AI is central, the algorithm recurses, well, if it recurses, it either finishes right there. It recurses on a set that is at most 3/4 the size of the current S. Okay? You got rid of a quarter, so the size of what remains is at most 3/4 of the size of what you're working on. So it's at most 3/4 S. So the conclusion that I want to draw here is that, so if, or you, being you or the algorithm, if the algorithm is in phase J when a central splitter is picked, then what? So we're in phase J. We're watching the algorithm go along, and it moves into phase J at some recursive call. And then we pick splitters, till finally we get a central splitter. And now what I'm saying is that the size of what you recurse on at that moment is at most 3/4 of the size of S that's in your hands. Okay? So what can we say about what phase we're in? Well, here S was between n to the 3/4 J plus 1 and n to the 3/4 J. It's in that range. Okay? Now we know that the new S when a central splitter, or I should say after a central splitter is picked, how big can it be? It can be at most 3/4 of what S was. That's how big it can be. S was at most this. So the new S, I'll call this S new, what can you say about its size? Yeah, the old one has this size at most. The new one is at most 3/4 the size of the old one. So its new size can at most be this times 3/4. 3/4 to the j plus 1. Okay? And what do we want to do on this side? It was at least this big. Okay. So, well, it was at least this big. Okay. But now it's smaller. Okay. So what can we say about how big it is at least now? Yeah, it's got to be j plus 2. That's all we know about it. We knew before that it was at least this big, and now it's 3/4 or less even of what it used to be. So all we can say about what it is n to the 3/4 j plus 2. Okay? So after you pick a central, if you're in phase j and you pick a central splitter, then the algorithm is in, well, I was going to put up the algorithm is in phase j plus 1, but it really depends on how much smaller it got. But it's certainly not in phase j anymore. Okay? All right, because in, yeah, in fact, when I say this is what we know, that's true, but we don't, that this is the best thing we can say, but in fact it might actually be smaller. Well, anyway, does everybody see the point that if the new one is less than or equal to this, okay, it's less than or equal to what was the lowest it could be when you're in phase j. So now you're less than or equal to that. So you can't be in phase j anymore. So let me get rid of this part because we don't need it. And I was a little bit unhappy with what I was saying when I wrote it up anyway. But this is enough to say we're not in phase j anymore. Because phase j is when the size of S is in this range, and now we know that the size of S new is less than or equal to this. Okay? And probably I should have been a little more careful about making this strict because we also got rid of AI. And then for sure there's no overlap between the size of S new and what this lower bound was. Okay? So the algorithm is not in phase j anymore. What phase is it in? It is in some phase greater than j. And again, I don't know for sure it's in phase j plus 1. It really depends on how much S really shrank. But what the analysis says is that it can't be in phase j anymore. It's got to be in some bigger phase. Okay, so I know there's a lot of pieces to this argument, but hopefully things are proceeding logically. Now I can ask, this is a question, what is the expected number of comparisons the algorithm does in phase j? Well, the algorithm goes into phase j, and then it finds splitters, gets smaller and smaller and smaller. At some point, it's out of the range that defines phase j because S is getting smaller and smaller. Now we know that if the algorithm picks a central splitter, it will get out of phase J. And we know the expected number of trials, number of picks until a central splitter is 2. And so we know the expected number of comparisons until a central splitter is picked is less than or equal to 2 times the size of S. Okay? So if you put all those things together, the expected number of comparisons where you're comparing an element to the splitter, so this is the answer to the question I just posed over there, expected number of comparisons in phase J is less than or equal to, again, the logic is this. You just entered phase J. You're going to pick splitters. As you're picking splitters, you're doing comparisons. And if the size of S is getting smaller, if the size of S gets outside of this interval, you're no longer in phase J. Okay? Second fact that we know is that the expected number of picks until a central splitter is 2. Third thing we know is that if you pick a central splitter, you will definitely get out of phase J. So the expected number of comparisons, you put all those pieces together, in phase J is less than or equal to, that's 2 for what it takes, the expected number of picks of a splitter until it's central. Okay. Then you're out of phase J, and while you're in phase J, the expected number of comparisons until a central splitter is picked is less than or equal to 2 times S. So what can I use for S here? What's the biggest that S can be when you're in phase J? Yeah. So n 3/4 J plus 1. No, J. Right. I think that's it. The expected number of comparisons in phase J is less than or equal to 2. That's the expected number of picks until you see a central splitter. When you pick a splitter, what are you doing with it? You're comparing it to every element in S. When you're in phase J, the size of S is in most of that. And when you pick a central splitter, you're out of phase J. So certainly by the time you picked a central splitter, you're out of phase J. So this is the total number of comparisons you did is less than or equal to that. Okay, let me ask a question. I'll put this on your homework tonight, unless it's absolutely answered in black and white in the text, but I don't think it is. In this analysis, we get out of phase J by picking a central splitter. When we pick a central splitter, we know we're definitely out of phase J. Okay? And that's why we have this 2 in here. This is the expected number of picks until you pick a central splitter. But what we're really interested in is number of comparisons in phase J. Do you have to pick a central splitter before you get out of phase J? That's one question you should be able to answer on your homework. And secondly, if you get out of phase J without having picked a central splitter, what happens to this analysis? Okay, does that corrupt things, or is this still okay? All right. So when you focus on that question, it'll force you to go through the analysis and understand all of the elements. All right, so the expected number of comparisons in phase J is bounded by that. Next we can ask, what is the expected number of comparisons done in the algorithm on a set S, where its size is going to be denoted as n. So how do you set this up? We know the expected number of comparisons in phase J. It's bounded by that. Oh, and I have to remind you of one more fact that comes from probability. One more fact. Okay. So we have random variable x1, random variable x2. Now let me be very, very specific. x1 is equal to number of comparisons done in phase 1. x2 equals number of comparisons in phase 2. xi equals number in phase I. Okay, so you're running the algorithm, and you note when you get into phase, well, you start in phase 1, or maybe it's phase 0. Anyway, you're in some phase, and you just note how many comparisons you do until you're out of it, and then you record that, and you record how many you're doing in each of the different phases. In some it's going to be 0 because you skipped that phase. And then you run the algorithm again, and you collect those numbers, and you run it again, you collect those numbers, and so on. Now, this is a random variable. It's just the number of comparisons were done in one experiment in phase 1, and so on. Okay, so what is expected? What's the expected value or the mean of x1 plus x2? Anybody remember from your probability class? Yeah, this is the second most important thing you learn in probability. I don't know what the first is, maybe just the definitions of things. This is the expected x1 plus expected x2. This is called the linearity of expectations. Okay, so you just get this nice decomposition. The expected value of the sum of two random variables is just the sum of the expected value of the two random variables. So you're running your experiment, you see how much x1 is, see how much x2 is, and you add those together, and that's your random variable. That's your value from the first time you do the experiment. And then you do the experiment again, running the algorithm, and you take this sum again, and you find out what that long-term average becomes. And analytically, you can prove that what you'll see, the expected value or the mean of that sum is just the sum of the two means. Okay, and of course it continues. So the expected value of the sum of xi is equal to the sum of the expected value of xi. Okay. What would happen, by the way, anybody remember, if I, instead of saying expected value, I talk about variance? The variance of two random variables? The variance of the sum of two random variables? Is that equal to the sum of the variances of the two random variables? Obviously, this is a question for people who've had a course in statistics and probability. Is what? Yeah, sometimes it is, but in general it's not. And there are some sufficient conditions, the ones called independence. But at any rate, in general it's not true for variance. So what we're seeing for expectation is very special. And it's true no matter whether these two random variables are independent or not. For any two random variables, this is true. But it's not true for variance and for other higher moments of the distribution. So, but at any rate, this is a true fact, an extremely useful one. So back to here. What is the expected number of comparisons done in the algorithm, in the whole algorithm, on a set S? So how do we set this up? Yeah?
2n multiplied by the geometric series 3 quarter sum from 3/4.
Okay, you got the right answer, but you're 2 steps ahead. I want to just go 1 step. I'm just...
Sum of the steps.
Yeah, okay. So, yeah, we're just going to sum over the phases. Okay? So we're in phase, I don't know, what phase do we begin in, by the way? 0 or... yeah, it should be 0 because this is 3/4 to the 0 is 1. All right, so J starts out at 0, and we'll just denote it by L at the moment. I don't know what that's going to be. We'll figure that out, okay? Or maybe we won't need to. But anyway, there's some number of phases, which is the largest possible number of phases. And in each phase, we know that the expected, in phase J, we know that the expected number of comparisons is less than or equal to 2 times n to the 3/4 raised to the j. Okay? And so, but what allows me to say that this is right? Okay, I'm just summing over the expected number of comparisons in each phase individually. Why is that the expected number of total operations in the algorithm? Because of the linearity of expectation. The expected number of comparisons done in phase 1 plus phase 2 plus phase 3, et cetera, is just the sum of the expected number in each phase. And that's what this sum is over here. It's the expected number done in phase J summed over the various phases. Okay? So if you set this up, if you just wrote this out, and you didn't refer to the linearity of expectation, it wouldn't be clear why that was the right answer. It may feel like the right answer. I mean, I think if I hadn't digressed and talked about the linearity of expectation, many people would have said this is the right thing to do anyway, just sum up what happens in each one of the phases. But it's really subtle. I mean, you need this kind of a fact to justify doing those sums. And I pointed out that for other functions of a sum, instead of expected value, like where the function is the variance, for example, you couldn't do that. It wouldn't be right to do it. But because we're talking about expected value, we're talking about mean, this is okay. All right, now L, we could figure out what's the biggest possible L, but I don't think we need to. All right? Yeah. I think we just need to remember some high school arithmetic. I'll take the 2n out here because that's constant. 3/4 to the j equals 0 through some number. Well, I mean, let's let it be infinity. Okay? So what happens to this? What's the sum of 3/4 to the j as j goes to infinity? Somebody went to high school. I know I didn't, but I know, yeah.
3/4 over 1 minus 3/4.
Yeah, okay. So this summation 3/4 to the j is equal to 1 over 1 minus 3/4. Okay? 1 minus 3/4 is 1/4, so that's equal to 4. So this whole thing is equal to 8n. So we have derived that the expected number of comparisons in this algorithm, and the algorithm, when is it doing comparisons? It takes a splitter and looks at all the elements in S, comparing them to the splitter. If you sum that up over the entire running of the algorithm, the expected number is less than or equal to 8n. Okay? 8n is theta n. Now, the analysis was sloppy in a number of places, but we always made the sloppiness on the right side. We always were looking for a bound from above on the number of comparisons, or the expected number of comparisons that were done. And whenever we were sloppy on the right side. So this 8n is actually, the 8 is probably too big. If you actually ran the algorithm that used to be here empirically and counted up the number of comparisons and ran it over and over again and took the average, you'd probably end up with something less than 8n. Of course, you'd have to do this as a function of n to actually see what the functional form is. But this is linear in n. And I mentioned last time that that's really kind of amazing. That's the best that you could hope for. You have a set, you have to read it in, you have to touch all the elements one way or the other, and yet you can find the kth largest, or let's say the median is the middle element, where the number of comparisons is proportional just to the size of the set. The other thing that's really interesting about this result is that we didn't make any assumptions about S except for what its size is. This is its size. Okay? So this expected value, the mean number of comparisons, is randomizing over the algorithm. It's the algorithm that's forming the source of randomness. The algorithm is picking randomly what that splitter is. We're not doing our analysis over random choices of what S looks like. So sometimes you can do an analysis that talks about, well, there's some probability that S is already sorted, or it's out of sorted by this, it's reversed in that probability, and so on. You make assumptions about what S is. This analysis was for any S. All we knew about it was its size, and the expected value here comes from the source of randomness, where the source of randomness is in the algorithm itself. And this is what's called a randomized analysis. When you randomize over the form of S, the form of the input, that's called a probabilistic analysis. So there's a slightly different terminology that's used for those two kinds of things. So whatever S you pick, when you randomize in the algorithm, you should get the expected number of comparisons that this should hold. And this also says that if you wanted to do this empirically, which you should do, I mean, it's a trivial algorithm to program, as long as you have a recursive language, which everybody does now. Has anybody ever programmed in something that wasn't recursive? Or do you even know what I'm talking about? Back in the old days, they had languages where you couldn't call yourself. It didn't have recursion built in. So if you ever wanted to implement an algorithm that's described recursively, you had to build in the mechanisms for that recursion, build the stack, unstack, etc. But now any language that you guys have programmed in, it's recursive. So you could program up select in, if there's, I'm probably the only person in this room who couldn't do it in 5 minutes. Okay, let's put it that way. Everybody here could just run out to your favorite computer and implement that in 5 minutes. And then the question is, if you wanted to see this result empirically, what should you pick as your set S? What would be a fair selection of the set S? This is another good question for the homework. Well, I'll give you the answer. Any set will work. That's what I was just saying. The source of the randomness in the analysis comes inside the algorithm. It doesn't matter what your set S is. You should still see this behavior. Okay? And so you can verify empirically that this is right. Okay. We have a couple minutes left. I was planning to go on to do randomized quicksort, whose analysis is very similar to this. It's just a little technically more involved. So, but now I don't really see the point. I mean, if I could do it in one lecture, that would be great. But I don't see the point now of essentially repeating this analysis with that additional technicality. However, that makes it seem natural for me to give you a homework question about randomized quicksort. So you can read that section. The randomized selection in the book merges in. The next section over is randomized quicksort. So I'll try to find a homework question that will ask you to read that section and answer a question about randomized quicksort. All right, I think the TA should be here shortly, and today's Monday, so I'll see you Wednesday.